Thanks very much, Fiona. Thanks very much, Brett and Philippe, for asking me to come today to talk about some of the stuff that we're trying to do in the more translational aspects of trying to treat inflammatory bowel disease. I'm interested in this, and so the way in which the normal colonic mucosa, for example, interacts with the normal immune cells in here in this situation of physiological inflammation, where the human gut immune system and the mouse gut immune system is highly activated, highly full of effector cells. And you can see this in the colon, but it's spectacularly shown in the small intestine, where you've got an isolated lymphoid follicle here with M cells in the little germinal center here, and you've got these ileal villi absolutely stuffed full of T cells. And understanding the biology of these cells and what they do in health and disease, I think, is key to thinking about the ways in which this can tip over from physiology into pathology. So, in fact, in many ways, the question that we're interested in is not really what causes inflammatory bowel disease, but why don't we all have inflammatory bowel disease? Because everything's there, the antigen's there, and the immune system is there. And people do use words like homeostasis, which actually, anytime one of my graduate students write homeostasis, and I score it out, I say, what does that mean? It doesn't mean anything. It just means balance. It's a non-word. So we have this situation, which is healthy, and we go to this situation, which is inflammatory bowel disease, which I think people, if look in mice, actually tend to underestimate the intensity and the seriousness of this lesion. I mean, we're talking actually about disease along meters of bowel frequently, especially for Crohn's disease. So here's ulcerative colitis, which is a neutrophilic lesion full of crypt abscesses and is organ-specific, and you can see this huge crypt abscess. And one tends to use the terms inflammatory bowel disease as a sort of catch-all thing, but essentially there has been very little conceptual understanding of what this organ-specific disease. No progress. All of the progress in understanding inflammatory bowel disease has essentially been to do with Crohn's disease. There are very strange things about ulcerative colitis. Like you're protected, for example, if you have your appendix out before the age of 20. If you smoke, you're protected. If you smoke 20 cigarettes a day, you're protected against ulcerative colitis. And so it's a very strange phenomenon associated with this complicated disease. It's somewhat less important because it can be cured by colectomy. But here's Crohn's disease, which is this particularly nasty disease. It's a mononuclear infiltrate. It has these terrible deep fishing ulcers that can come through and penetrate through the mucosa. It's full of granulomata, the stigmata of T-cell immune responses. And also, I think interesting, these ectopic lymphoid follicles forming deep in the mucosa. Is this where memory exists? Is this actually, what is the role of these? These are down deep in the muscle layers. And no one ever knows if these go away when patients go into remission. I think it's a very interesting point. Now, to think about the way in which physiology turns into pathology, I think we've been making some studies actually of what happens actually about mucosal immune responses. And there's no doubt that actually that the compartmentalization of the immune system in the gut is absolutely critical towards what happens here. If you want to understand what happens here, you have to understand what happens here. And the Peyer's patches in the organized lymphoid tissue, because this is the inductive site of immune responses. This is where all the retinoic acid, etc. is. And this is also where antigen comes across. There's very few goblet cells here. There's none along here, allowing access of antigen to get across. You can stimulate these, the germinal center, and the T and B cells migrate around and go into this compartment. Now, I have credentials actually as a gonotobiologist. I mean, I think, although I'm talking about mice, I've actually made germ-free mice. I've done it. I've had my hands in the isolators and have suffered respiratory disease because of peracetic acid. And this is some germ-free mice that I made in America in the 70s, funnily enough, actually. And you can see germ-free mice, Dormouse germinal center, germ-free mice, indolent immune system actually with primary follicles. And because the cells migrate out, you don't need immunohistochemistry to show this actually. So here's a germ-free mouse. They ain't got any immune cells in their gut. There isn't any. And here's a normal mouse. And if anyone knew histology anymore, that's a plasma cell there. That's a lymphocyte. So you don't need markers to tell them. So clearly the flora is driving all sorts of immune responses. And we've done quite a lot of work in newborn babies and the fetus. And this happens in people as well, actually. You're born IgA deficient in people. So. So when you're thinking about the effector site of the gut, you've got to think about how all these activated cells are migrating around the body, going into the gut, making gamma interferon and IL-17. And in fact, if you go into the human gut and take a biopsy from any person in this room and plug it into early spots of PCR, what you find is actually a very strong effector site with tons of cells making gamma interferon and very, very few cells making IL-4 and IL-5 and IL-10 or TGF-beta or anything else for that matter. And these cells die. They die, they turn over very rapidly. They probably live for no more than a day. And things like TGF-beta coming across can switch these cells off, and there's no antigen. And important, there's no survival cytokines. There's no IL-17, there's no IL-15, there's no IL-12, there's nothing in here. So these cells are moving along and dying. So when you cut a picture, a histology picture of a gut, and you see lots of T cells, there is a sort of feeling of permanence about these cells. These are gone, coming and going away. And it's just typical of the immune system to be, just ridiculously wasteful. We make lots of cells, and I think the important thing is the intact barrier. Not a lot of antigen gets through, especially across the mucus. And as much as you can do an experiment in people, which is kind of hard, but you can do sort of schlocky experiments, and you can take bits of biopsies and lamina propria mononuclear cells out of Crohn's disease patients, or normals in this case. And you can just throw in some anti-TGF-beta-1. And what you can see is actually gamma interferon goes up, IL-2 goes up, IL-8 goes up, IL-17 goes up, everything goes up. If I wanted to make this go up really, really high, I would put in some IL-12. Really good, that I could make this go up to thousands and thousands of picograms with IL-12 because the cells are activated, they express the high affinity receptor. And we know actually that this is a Tibet-driven thing, and if you sort of add anti-TGF-beta and just do some blots to see what happens, the cells all die when you put them in with IgG, so obviously there's nothing much happens here. Putting an anti-TGF-beta, they still remain the signature cytokines. And it's actually the same for ROR gamma T as well. We've done that, but let me show that. T17. So we believe actually that TGF-beta plays a major role in controlling the immune response in the gut wall, and one of the reasons is actually because this paper 20 years ago, TGF-beta null mice die, and also Fiona's shown that T cells making TGF-beta control immune responses in colitis, so I think that's good reading. But the question is, where does it really come from? Is this is a sort of a specific response, or what's going on here? The major source of TGF-beta in the human gut by tens of thousands of fold is the gut epithelium. The gut epithelium is absolutely stuffed full of TGF-beta, which I've drawn in grey here. And because the gut epithelium expresses alpha V beta 6, it's making active TGF-beta all the time. Ridiculously high number of transcripts. And actually, this TGF-beta is coming along all the time. A lot of TGF-beta made by fibroblasts as well. And actually, we think it's dampening the immune response. And there's some quite nice, interesting mice that have a TGF-beta depletion in the epithelium, and the signatures of TGF-beta responsiveness disappears in the lamina propria. So we think actually there's a dampening of the immune response by TGF-beta. Now, I've sort of felt a bit equivocal about IL-10 actually, simply because I was involved in the IL-10 trials, which were infused IL-10 into Crohn's disease patients, and it didn't do anything at all. I mean, it was an absolute failure, but I think I'm not sure whether I should put a macrophage in here or not, but I do think this is important because there's something dampening it because of this paper in the New England, which is a really important paper. And there's another really important paper out in Science, actually, from Paris. Casanova has just shown that IL-17 knockout people get chronic mucocutaneous candidiasis. That's just great. That means it's important. I had my doubts about IL-17 before that. But anyway, you can see, actually, that there's this tremendous lesion, actually, this terrible, thickening of mucosa, looks like Crohn's disease. So clearly IL-10 does play. And the mind, it's sort of good to see that the humans occasionally behave like mice. Happens periodically. And I was looking through the literature, actually, and funnily enough, I saw this thing by the Mizoguchis, which just appeared. And these are all the animal models of IBD, which actually, I don't really care much about all the different models, but in fact, I do like the fact they've got SMAD3, TGF-beta, and IL-10 in the middle, actually, which makes me very happy. So clearly, there's very discerning people. They know what's important, actually. They know that TGF-beta is very important in these things. Okay. Now, it's one of the interesting things in which the way in which research goes that there's been, the genomic initiative actually for understanding these things have become these complex diseases have been very important, actually. But you see things like SMAD3 has popped up there, which made me feel very happy. There is a big issue, actually, about how we're going to deal with this data on a global level. We've got too many hits with low effects, actually. And so the question, well, this is interesting and giving us sort of quite clues. There's IL-10 popping up as well. How are we going to take this information forward, actually? Because there isn't enough money in all of the world to support projects to dissect out every one of these. There just isn't. There's not the funding around, actually. So we all pick our favourite one and then just go ahead and work on that. That's how people do it. So I want to talk about the stuff we do in Crohn's disease. So in Crohn's disease, the problem is there's chronic T-cell activation in the gut wall. There's a damaged barrier, which might be primary. Gut bacteria coming across, we think. I mean, just actually look for the data on this, actually. It's not really very solid. And actually, there's a lot less TGF-beta, and the T-cells survive. They don't die, and they keep on making cytokines like TNF-gamma, IL-17, and whatever, actually. They just keep on going. And it's an accumulation of activated T-cells in the gut wall. And there's as much, this is work that Laura Rovidati did in the lab, actually, but there's as much IL-17A, and quite a lot of IL-17F as well, in inflammatory bowel disease, especially Crohn's disease, as in ulcerative colitis. So this is CD3, CD28 stimulated cells. And you can see the gamma's up here, about 7,000, but this is actually just slightly lower than that. So there's a lot of IL-17. There's quite a lot of IL-17F as well. IL-25 has gone down, we've published that. So there's a lot of IL-17 in these tissues. So, and of course, the microbial flora is everyone, which is what this meeting is about. But, the question is really, well, I think the experiments are fabulous. And as a notobiologist, I really love to see the fact that notobiology has come back again. Because I think that the way in which this is going to be translated into therapy for Crohn's disease, and also it's going to be quite a way away, actually, although lots of people are working on it. So I just still think that they've got to hit the immunology, essentially, and start thinking about the disease. So we know the T cells start the inflammation, and down here they're making IL-17 and gamma interferon cytokines. Lamina propria fibroblasts are actually responding to TNF and other things as well, making these enzymes that degrade the gut wall, matrix metalloproteinases. And here's an ulcer here, surrounded by MMPs. So the immunology starts, and then end-stage effectors common to the skin and the joint and the brain and everywhere, all cut away. So I wrote something actually just before Christmas, because I was spending a lot of time thinking about this, actually, this is a summation of lots of animal, lots of animal data, which actually is these things about a few of the T-cell related molecules critical in mouse and human IBD. And this is actually, a lot of people have put a lot of work into this and been very, very good papers. Is there a peptide in which has been presented to the T cells in the gut wall? I don't know. No one's ever shown that, actually. We assume that's the case, but we don't actually know it. What the contribution of IL-2, IL-21, epithelial-derived cytokines as well, and all these effector cytokines on all the adhesion molecules. And the squares I've chosen here are the things which actually didn't work, although they should have worked. So IL-12, 23 actually didn't work in Crohn's disease. The first study was too small. It was in the New England, and it didn't hit an endpoint. And omalizumab, which is actually the Johnson & Johnson anti-IL-12, IL-23 P40 antibody, they're dropping it. It didn't work. They got a hint of a response in TNF-experienced people, but they're not really happy about that. IL-17 was bad. It was reported in Dublin at the ECHO meeting that it made people worse, actually. And 3 studies of anti-gamma interferon antibody were completely negative, not a little bit negative, really, really negative. There was not a sniff in any subgroup analysis. And the question is really, what's going on here? And for drug companies, the question is, who should we chase? Who should we listen to? What are we going to do to try to spend $60 million taking, another anti-IL-6 into patients and find that it doesn't work? It's a very, very important issue for translational research. And in fact, we probably got carried away with anti-TNF antibodies because they work because they're T-cell depleting. They kill cells expressing membrane TNF. At least that's what it says in the books. Okay. So I think we need to think a bit more broadly and what keeps the bowel healthy. And I told you it was TGF-beta. So we've done a lot of work on TGF-beta signaling in the gut wall, and this sort of summarizes lots and lots of papers. in the normal gut, the abundance of TGF-beta, no matter where it comes from, is actually a very effective molecule at switching off T cells and macrophages. So it signals through the TGF-beta receptor, activates the canonical SMAD signaling pathway, and just represses genes. That's what it does. So if you take a Th1 cell, add TGF-beta, it stops making gamma interferon. You know. But in Crohn's disease, and I don't know why this is green, it's supposed to be red, what happens is the TGF-beta comes along, sorry, I've got the wrong slide here, and the presence of SMAD7 in the cell makes the cell continue to make cytokines, and you get continued T cell production in the gut. And that's a very bad thing. SMAD7 is a very bad molecule to be overexpressed in cells because it makes them unresponsive to TGF-beta. And these are the best experiments I've ever done in my life. Actually, this is just great experiments. So you can just do simple blots of biopsies, and you can take control mucosa, and there's an endogenous level of TGF-beta signaling because the TGF-beta is talking to the cells and dampening down. Add some TGF-beta, nanogram per mil, and you get a big activation of phosphosmad3 showing its signaling. And you try and do it with inflammatory bowel disease patients, and it doesn't work. They're completely unresponsive, and they're unresponsive because of SMAD7. And so we know that we can knock down SMAD7 because SMAD7 blocks TGF-beta signaling by sending the receptor off to the proteasome and also physically blocking the recruitment of SMAD2 and SMAD3. And if we use an antisense to SMAD7, we can knock it down in cells from patients. And without doing anything, SMAD3 pops up again because endogenous TGF-beta in the tissue is then starting to signal to the cells. And the denouement is to do this experiment in samples from Crohn's disease patients by putting them in culture and adding an antisense to SMAD7. So the idea is you're releasing the cells from the brake that SMAD7 is putting on them, and actually you just do some simple blots. What you find in the tissues as well, you can knock down SMAD7, endogenous TGF-beta activates SMAD3, phosphosmad3, total SMAD3, and down go the cytokines, TNF and gamma interferon, medium sense and antisense. The SMAD7 is really, so this is a great experiment. This is the presence of SMAD7 and T cells in the gut has actually got all sorts of implications for the treatment with Tregs, although it's something that we're actually going to be doing actually in London. Because the question is, will Tregs, which work by making TGF-beta, don't know about IL-10, will they suppress activated T cells from Crohn's gut? And so we can do little experiments, and this is what Massimo did. Actually, so what we did, you can take blood Tregs and blood T effectors and mix them up at different ratios and measure proliferation and cytokine production. And you get a lovely suppression. This is a classical suppression assay down to about 50% suppression. This is what everybody gets. You can take blood Tregs and ask them if they will suppress T cells from normal human gut, and you get the same response. You can take blood Tregs and ask them to suppress Crohn's disease T cells, and they don't do it. And the reason they don't do it is because the cells express SMAD7, because if you knock down SMAD7, they become effectors again. So I think that, now despite this, my positive predictive for predictions for experiments in my lab are a disaster. Whenever I tell a student, don't do that, and it always works. So despite the fact that I really don't think that Treg therapy is going to work in inflammatory bowel disease, the fact is we have to do it anyway. And so the GMP facility over at Guy's Hospital, where we're growing up Tregs, and we're going to put it into people and see if it works. It might work. I think it's an experiment that's got to be done eventually, autologous Tregs. One of the things the Americans like is to make mice, so Massimo also made a mice. I don't know where this comes from, this thing about you do a good experiment on people and they don't believe it unless you do it in a mouse. So Massimo made a mouse expressing SMAD7 on the CD2 promoter, and we put it into Fiona's assay. And we just took normal T effectors and normal Tregs, and they don't get any colitis. But if you use SMAD7 T effectors, they still get colitis. And you can see the lesions here. And that's because the cells expressing SMAD7 are not amenable to receiving a signal from T regulatory cells. So I think that pathogenic T cells swimming in a sea of TGF-beta, but essentially they can't hear them as long as SMAD7 is there, and we've got to do something about that. Now, the reason actually this is, I would say it's important, is because this has been taken into phase 1B trial. So Giuliani have made, who are very good at drug delivery in the gut, have made GMP-graded antisense to SMAD7. And it's been given to 15 patients, and another And a phase 2 trial, a proper RCT, is underway with real placebos. And the results were spectacular, actually. 13 out of 15 patients went into clinical remission, which actually meets the 80% thing you need in an open label before anything will work in an RCT, which is actually what the experience has shown over the years. So it's just very, very interesting, actually, that by putting SMAD7 in, dampening it down, endogenous TGF-beta will allow the gut to heal itself. And I think it's a good idea, and I'm very pleased, actually, it's going into patients at long last. It's taken us a while. It's very expensive. Right. So, now we still do face these issues, though, about whether we should have our favourite cytokines. You know, I mean, we all do it. Immunologists all love I love TGF-beta, you know, and there are IL-2 people, IL-7 people, you know, they have a passion. Rick Blumberg loves IL-27. Right. So I'm going to try and persuade you, actually, that despite what I said about, I think that maybe none of these things might work, or a combination therapy or something, that this molecule here, IL-21, is probably worthy of a sniff, because of all of these things, I think IL-21 is probably going to be more important than, at least I say that, but and I believe it, I think. Anyway. IL-21 is a very interesting molecule, actually, because it's made by CD4 cells, and it helps all sorts of lineages, actually, and it's important in long-term immunity viruses. But actually, and it's also, as we've seen before, it's also very important for Th17 cells. More of a maintaining factor for Th17 cells in people, and it's mostly made by Th1 cells in people, actually. But so what about IL-21? IL-21 is very overexpressed in inflammatory bowel disease. So this is before the ELISA was available. You can see actually just blotting for it in inflammatory bowel disease. There's a lot there, and there's some in controls. So we did quite a lot of experiments, actually, trying to see if we neutralized IL-21 in samples we taken from Crohn's disease patients, could we really knock down gamma interferon and IL-17? And we've just taken cells from patients and added anti-CD3 to give them a kick and neutralized IL-21 here with a receptor fusion protein and with an anti-IL-21. And, you know, the experiments were done 20 times, so we could never get better than this. And on this data, you would actually say that, well, actually, anti-IL-21 doesn't look a very good candidate to go into patients. Why would you do it? You know, it's really not very effective to get rid of these effector cytokines, although knocking these down didn't make any difference either. The reason why we're slightly more enthusiastic about IL-21 is it does other things, which are all very bad for the gut. So a T cell making IL-21 in the gut, it can maintain gamma interferon IL-17, so hopefully they'll knock that down by 50%. But it's a very potent inducer, actually, of CCL20 by epithelial cells. So it drags a lot more T cells in from the gut, which is not into the gut. And finally, it's very, very potent activator of metalloproteinases. So IL-21 binds onto the receptor, and these start chucking out huge amounts of MMPs. And we think that must be a very bad thing, because they digest the basement membrane, and the epithelium falls off, and more antigen can get in. So I think these other things, actually, are probably more important. We also did the de rigueur experiments, actually, which we have to do. We got IL-21 null mice, and they don't get DSS colitis. Here's IL-21 knockout mice, and here's the things. We're getting a bit fed up doing these experiments, actually. They always work. Here's IL-21 mice protected from TNBS colitis as well, because you don't have to do it in one model. You've got to do it in 2 models now to get into gastroenterology, which I think is really pushing it a little bit. So the question really is, we think, actually, that IL-21 would be a good thing in Crohn's disease. We think because of the 3 reasons. It reduces Th1 and Th17 cytokines. It stops IL-21 inducing stromal cells to make MMPs, and it stops epithelial cells making CCL20. And what we're going to be doing is we're going to be putting it into patients. So we're working with Novo Nordisk, who've got a humanized anti-IL-21 antibody, and we'll put it into people and see if it works. And that, in the end, will be the proof of the pudding. We'll know, which I think is fair enough. Okay. So I think that although there's been, I think the work in ILCs is just fabulous. I mean, I'm just overwhelmed by the quality of the work, actually. I think in an intact immune system, I still think the T cell is the target, actually. And I think there are all sorts of reasons, actually, because the T cells responding to the microflora have got a problem. They've got memory, and I think memory is a nuisance, you know. And we now know that we can, you know, we're quite a successful treatment, although too dangerous for Crohn's disease, actually, to give them a bone marrow transplant. And there's a European-wide program been doing that, actually been recruiting patients, and essentially reprogram the immune system and take it back down and start it all over again. And I think there are some quite clever ways in which we can hit the T cells rather than thinking about the cytokines to produce, to actually reprogram that T cell and hopefully make it die. And we're working on that as well, but I don't know if that'll really work or not. So anyway, this is who supported the work. The European Union, Medical Research Council, the Wellcome Trust, and a charity. I spend a lot of time in Italy. I've got very strong Italian connections. These are Italians in my lab, and these are the Italians in Italy, especially Giovanni Monteleone, who I've been working with for a long time. And we couldn't do anything, actually, at all, not a single thing, without the boys and girls hanging around the theatres, just picking up little bits of tissues as they come out of patients so they can try and do something. And these are the people that enable this sort of translational research. So I'll finish there. Thanks.